All right, there is a hidden, incredibly high-stakes battle constantly being waged right above our heads and right beneath our feet. I mean, we completely take it for granted that when we flip a switch, the lights just come on, right? But the power grid is an incredibly volatile beast. We're talking about massive amounts of unpredictable, highly destructive energy flowing at all times. So what happens when something actually goes wrong? What stops that invisible energy from just tearing through and destroying everything in its path? Well, let's find out. Picture this for a second. A massive storm rolls through. The wind is absolutely howling. And suddenly, a huge oak tree snaps and crashes directly onto a high-voltage transmission line. Crack! Sparks are flying everywhere. You have tens of thousands of volts suddenly finding a new unintended path straight to the ground. In literally a fraction of a second, the current spikes to catastrophic levels. Now, if that energy is left unchecked, it's going to literally melt multi-million-dollar equipment, spark massive fires, and cause a cascading blackout that could plunge entire states into total darkness. But that almost never happens. Why is that? What invisible force steps in to stop the entire grid from burning down? Okay, let's dive into this. The real hero of our story is something called a protective relay. It's basically an incredibly intelligent sensing device that acts as the absolute brain of the power grid security system. Its whole job is just to sit there 24/7, continuously monitoring electrical parameters, things like current, voltage, frequency, and phase angle. When that tree falls and causes a short circuit, or what engineers call a fault, the relay instantly detects that something is wrong. But here's the cool part, it doesn't just panic and sound an alarm. It actually calculates the severity of the problem, pinpoints the exact location, and decides exactly when and how to isolate the faulty section. It is the ultimate grid decision maker. Section 1, the relay roster. So to really understand how these devices protect our grid, we gotta look at how they've evolved, because we definitely didn't always have supercomputers running the show. The older generation relied on electromechanical relays. These were classic, rugged physical devices that used magnetic induction to literally move mechanical parts and close contacts. They were tough, sure, but physical parts take time to move. From there, we upgraded to solid-state or static relays, which swapped out the moving parts for electronic circuits, think transistors and diodes, to process signals way faster. And that brings us to today's modern standard, numerical or digital relays. Honestly, these are basically high-powered computers. They sample analog waveforms, convert them into digital data, and use advanced software algorithms to spot faults instantly. Plus, they can run their own self-diagnostics and talk to the rest of the network. It's a massive leap forward. Now, what's really interesting about this slide is how we can categorize these modern relays by their highly specific tactical functions. They're like specialized agents on a roster. First up, you've got overcurrent relays. It does exactly what it sounds like. If the current pushes past a certain threshold, it trips. These are the bread and butter for local distribution networks. Next, we have distance or impedance relays. These use a specific math formula, measuring voltage divided by current to calculate the exact distance to a fault. They are the absolute backbone of high-voltage transmission lines. Then there are differential relays. The logic here is simple but brilliant. They measure the current entering a specific zone and compare it to the current leaving. If the difference isn't zero, it means energy is leaking out somewhere inside, like inside a giant transformer, and it trips instantly. Finally, directional relays make sure trips only happen if the fault current is flowing in a specific direction. That's absolutely vital for preventing unnecessary outages in complex, looping grid networks. Section 2, the high stakes of grid failure. To really appreciate this roster of devices, we have to understand exactly what happens if they fail. The consequences are, frankly, terrifying. And that's exactly why they're programmed to guarantee 4 vital outcomes. Number 1. Isolation of faults. They make sure only the damaged component, like that one specific power line hit by the tree, gets disconnected. The rest of the grid stays energized, which minimizes those annoying blackouts. Number 2, equipment protection. We're talking about stopping multi-million-dollar generators and transformers from literally melting down or catching fire by clearing the short circuit instantly. Number 3, personnel safety. This one is life and death, guys. Rapid clearance minimizes the risk of lethal arc flashes and high step voltages that could severely injure utility workers or anyone just standing nearby. And finally, number 4, system stability. Our power grid is heavily synchronized. Fast-acting relays keep the whole system perfectly balanced, preventing a localized voltage drop from spiraling into a devastating, cascading system failure. Section 3. The ultimate tag team, brain meets muscle. Now, the relay is just the brain, right? It calculates, it thinks, but it doesn't actually have the physical power to stop a massive surge of electricity. That requires the ultimate tag team. On one side, you have the distance relay. This is the brain. It's crunching the numbers, acting as the detective, identifying the exact nature of the problem. On the other side, you have the circuit breaker. This is the muscle. Once the brain figures out there's a threat, it taps the muscle to bring the brute physical force required to actually halt that massive fault current. They are completely and utterly dependent on each other to save the grid. And this brilliantly illustrates exactly how the brain figures it out. Think of the distance relay as a detective, and honestly, it uses high school math as its primary clue. The relay is constantly dividing voltage by current to figure out the line impedance. Under normal operations, impedance is nice and high. But when a fault happens, like when that tree comes crashing down, the voltage sharply drops and the current massively spikes. That means the calculated impedance suddenly drops. Because line impedance is directly proportional to the length of the transmission line, the relay instantly uses this mathematical clue to calculate exactly how many miles away the bad guy is. It isolates the exact location of the threat in real time. It's incredibly smart. Let's move to and see how this builds into real-world action. Here is the rapid, 4-step sequence of how the brain and muscle actually work together to isolate a transmission line fault. Step 1 is sensing. Current and voltage transformers step down the massive grid power to safe, measurable levels so the relay can actually see what's going on. Step 2 is decision-making. The relay runs its math, sees that sudden impedance drop, and realizes, uh-oh, a fault has occurred within my protected zone. Step 3 is the tripping circuit. The relay's internal logic physically closes a contact, completing an external DC circuit powered by a heavy-duty battery bank, which sends a high current pulse straight to the circuit breaker. And finally, Step 4, interruption. That pulse energizes a coil in the breaker, acting as an electromagnet, unlatching a mechanism. Then powerful, pre-charged springs instantly snap the heavy breaker contacts apart, physically breaking the circuit and extinguishing the electrical arc. Boom, threat neutralized. So the crucial point is, how fast does all of this happen? I mean, from the exact moment that tree touches the wire, to the transformers stepping down the current, the digital relay doing the complex math, closing the contacts, sending the DC pulse, the electromagnet unlatching, and those heavy mechanical springs snapping the massive contacts apart to extinguish a deadly arc, all of that whole shebang happens in less than 50 to 100 milliseconds. A literal blink of an eye. No way, right? But it's true. It is a staggering mechanical and computational miracle, and it's happening constantly all around us. So as we wrap up this explainer, I want you to just take a look at the screen you're watching this on. Look at the lights in your room right now. How are these invisible brains and muscles working out there in the elements at this very second, sensing, calculating, and waiting to protect the grid that powers your entire life? It's an absolutely incredible hidden world out there, and without those 100-millisecond lifesavers, we'd truly be left in the dark. Thanks for joining me on this explainer, and keep asking questions about the invisible world around you. Catch you next time.